Welcome everyone. So today we're going to discuss about state potential barrier. A state potential barrier in quantum mechanics is a potential energy profile that has a certain continuous jump to a new constant value. Suppose there is a potential V naught at x equals to 0. So the particle, whenever the particle is in this region at x less than 0, here the potential V is 0, but whenever the particle reaches this region at x equals to 0 or maybe x greater than 0, this region, it will have to encounter this potential V0. So this type of case is called as state potential barrier. Here there is a continuous jump to a new constant value in potential. So this is state potential barrier, and it is used to model situations where quantum particles like electron faces a region of higher potential energy. But here the key difference between classical mechanics and quantum mechanics is that the quantum particles have a non-zero probability of being transmitted and reflected back by this potential irrespective of their total energy. So the quantum particles have a non-zero probability of being reflected or transmitted by this potential irrespective of their energy. So how is it possible for the quantum particle of being reflected or transmitted even when their energy E is less than this potential V0? But how is this possible? We're going to see this by doing the details calculations. So a single state barrier is shown in the figure, and it is represented by V of x is 0 for x less than 0, and it is V0 for x greater than 0. So denoting the wave function in the region x less than 0 as psi 1 of x, and for x greater than 0 we're going to represent the wave function as psi 2 of x. Now we are going to consider two different cases where the energy of the particle E is less than V0 and where the energy of the particle E is greater than V0. Okay, so for the wave function psi 1 and psi 2, we can write this Schrödinger equation as minus h square square by 2m d2 psi 1 dx2 is equals to E psi 1, and minus h square square by 2m d2 psi 2 dx2 plus V psi 2 is equals to E psi 2. Now we are going to consider two different cases. First we are going to consider case 1 where the energy of the particle is greater than V0. That means E is greater than V0. Now we can rewrite the equation 1 and 2 as d2 psi 1 dx2 plus 2m E by h square psi 1 is equals to 0, or d2 psi 1 dx2 plus k1 square psi 1 is equals to 0. Here k1 is equals to 2me by h square. We can also rewrite equation 2 as d2 psi 2 dx2 plus 2m by h square into e minus v0 into psi 2 equals to 0, or we may write it that d2 psi 2 dx2 plus k2 square psi 2 is equals to 0. Here k2 is equals to 2m by h square into e minus v0, this term actually. Now the general solution of the above two equations is psi 1 equals to a e to the power I k1x plus b e to the power minus I k1x, and psi 2 is equals to c e to the power I k2x plus d e to the power minus I k2x. Here this a e to the power I k1x represent the incident wave, b e to the power minus I k1x represents the wave reflected from the barrier, and c e to the power I k2x represent the emitted wave into region x greater than 0, and d e to the power minus I k2x represents the wave which we get reflection into barrier which does not exist. So d is equals to 0. Now we need to calculate the values of b, c and a. Now we have our two expression of wave function psi 1 and psi 2 in this form. Now we need to calculate the value of b, c and a, and in order to calculate the constant b and c in terms of a, we need to consider two conditions. Condition 1 is that the wave function psi must be continuous at the boundary x equals to 0. So if we put x equals to 0 in the expression of psi 1, we get psi 1 equals to a plus b, and if we put x equals to 0 in the expression of psi 2, we get psi 2 equals to c. So by using this condition that the wave function must be continuous at the boundary, we get psi 1 of 0 equals to psi 2 of 0. That means a plus b equals to c. So we are going to consider the next condition now. Now the second condition is the first order derivative of d psi by dx must be continuous at x equals to 0. So this is our second condition, that the derivative of wave function, first order derivative of wave function must be continuous at x equals to 0. So applying this condition on psi 1 and psi 2, we get d psi by dx at x equals to 0 is equals to d psi 2 by dx at x equals to 0. So if we do the derivative and put x equals to 0, we're gonna get k1 into a minus b equals to k to c. That means a minus b is equals to k2 by k1 into c. We're gonna name this as equation 9. By solving 8 and 9, we get the values of c and b in terms of a. If we put these values on the expression of psi 1 and psi 2, we get the expression of psi 1 psi 2 in this form. Now the incident wave is psi in, which is a e to the power I k1x, and the probability current density for incident wave is J in. So using this formula and the expression of psi in as a e to the power I k1x, and putting this in this formula, we get the value of the probability current density for incident wave as h cut k1 by m mod a square, and the wave reflected back is psi r, which is b e to the power minus I k1x, and if we calculate its corresponding current density, we get Jr, which is h cut k1 by m mod b square. And similar way for the wave transmitted into region 2, which is psi t, that is c e to the power I k2x, and if we calculate its corresponding current density, we get Jt, which is h cut k2 by m mod c square. Now these are the three expression of probability current density for the reflected, incident and transmitted wave. The reflection coefficient R, which is the probability current density of the reflected wave and the probability current density of the incident wave. That means Jr by J in, and putting the values of Jr and J in as we have calculated previously, we get the expression of R in terms of K1, K and K2 in this way. And similarly for the transmission coefficient, which is the ratio of the probability current density of the reflected wave and the probability current density of the incident wave, that means Jr by J in. So putting the values of Jr and J in, we get the values of T in terms of K1 and K2 in this way. And one thing we need to notice is that if we add R and T, we get 1. So adding R plus T, we get 1. Thing we need to notice is that if we add R and T, we get 1. So R plus T is 1. This is the proof of the conservation of probability at the boundary. We are going to consider case 2 when E is less than V0. So in case of E less than V0, we can write our Schrodinger equation for psi 1 and psi 2 in this form, where K1 and K2 are 2m by h cut square into E, and K2 is 2m by h cut square into V naught minus E. So the general solution of these two equations, equation 17 and 18, is psi 1 equals to a to the power I k1x plus b to the power minus I k1x, and psi 2 is d to the power minus k2x. So now to calculate the constant a, b and d. So now to calculate the values of a, b and d, we need to apply two conditions. Condition 1 is that psi must be continuous at boundary, that is psi 1 of 0 is equals to psi 2 of 0, which is a plus b equals to d. And the second condition is the first order derivative of psi, that is d psi by dx, must be continuous at the boundary. That means d psi 1 by dx at x equals to 0 is equals to d psi 2 by dx at x equals to 0. Applying these two conditions on psi 1 and psi 2, we get equation 23 and 24. And after solving equation 23 and 24, we get d equals to 2k1 by k1 minus I k2 into a, and b is k1 minus I k2 by k1 plus I k2 into a. The incident wave function psi in is a e to the power I k1x, and the probability current density for the incident wave J in is h cut k1 by m into mod a square. Similarly, the reflected wave psi r is b to the power minus I k2x, and if we calculate the probability current density for the reflected wave, it is Jr, which is h cut k1 by m mod b square. So the reflection probability R, or the reflection coefficient R, is equals to k1 minus I k2 by k1 plus I k2 mod square, which is 1. And the transmitted wave psi t is 2k1 by k1 minus I k2 e to the power minus k2x. Here the reflection coefficient R is equals to 1. That means we get total reflection as in case of classical case, but there is a difference between the classical case and the quantum case. Classically, we cannot find any particle in this x greater than 0 region, but quantum mechanically the transmitted wave psi t is this, and the probability, its corresponding probability, is mod of psi t square, which is non-zero. So quantum mechanically we can have particles in this classically forbidden region, this x greater than 0 region, irrespective of the energy of the particle. So this was the difference between the classical and the quantum case. Okay, so now we can see the behavior of probability at these two regions from this diagram, and the behavior of wave function in region 1 and 2 for E greater than 0 and E less than 0. So this was our discussion on state potential, and on our next class we're going to discuss about the operators in quantum mechanics. Thank you everyone.